Well, hi everyone. Let a few people get in here. See a couple are waiting, so we'll go ahead and give them a chance to come in. Today I thought that I would do something that I did on TikTok yesterday, but I'm going to try and do it again today and do it better. This is the mathematics of the eclipse of April 8th. Now, I don't know how many of you are going to be able to see the eclipse here in North America, but my wife and I are actually going to drive a couple of hundred miles south to get into the area of totality. And I'm going to try and live stream it using two telescopes. One is a white light telescope, which will be the best one to see the actual eclipse occurring. And then I'm also going to kind of bolt the hydrogen alpha telescope on top of it, and we'll get a dual monitor view. If that depends on me being able to get to some power and be able to get internet access, which can be an issue. So let's see, who do we have in here? Hey, Real Cygnus, how are you today? Judy's here too. We have a big problem, so I brought my big slide rule with me. That's the 7-foot picket. It's a version of this one right here. But that's the 7-foot picket that I'm going to use when I eventually start teaching this sort of stuff. And I got that from a guy down in North Carolina that had it sitting up in his, from the rafter, hanging from the rafters in his workshop. Didn't really want to do anything with it, and just basically wanted to get rid of it. So he gave it to me for a song and shipped it up here to me, and it arrived today. So I'm real pleased with it. Everything works on it just fine. It's even got a little slide, actually a big slide. So that's a fully functional slide rule, and it seems to work pretty well. Is my audio a little too loud? It's looking like it might be a little loud, and I'm wondering, am I getting a bit of an echo there at all? There we go, a little better. Yeah, it's pretty nifty. It's a Picket N500 ES iSaver yellow. And like I said, it's basically this slide rule right here, which is one of the ones that I recommend. The other one is this one, which is the Picket N3, and that's kind of my daily driver. I have other slide rules. I've got 20-inch slide rules. I've got an N83 by Castell, which is probably the best slide rule ever made. But my daily drivers is this one right here. It's solid aluminum. It's made by an American company called Picket. It was built in about 1960 or 62. This thing's as old as I am. Still looks new. I wish I could say the same for me. All right, so we have an interesting opportunity coming up for those of you that can see the eclipse and maybe know some people that are going to watch it from a different location. We can actually determine the distance to the moon. Now, let me go ahead and I'll show you basically how that's going to work. You guys let me know if you can't see this very well. All right, it's close enough for you. I can probably zoom that in just a hair, or not. Maybe I can do it here. Dump, boink. We'll bring that up just a little bit to make it a little easier to see. How's that? All right, so let's go ahead and kind of go over a couple of things real quick. First of all, anybody have any questions to get started? All right, so now the first thing that we have to understand is that the sun and the moon move across our sky at a different rate. The solar tracking rate is 15 degrees per hour. Now the moon, because not only are we dealing with the orbit or the rotation of the Earth, we're dealing with the orbit of the moon itself. The lunar rate is a little bit less. It's actually 14.685 degrees per hour. And as a result, there's a difference of 0.315 degrees per hour. So the sun actually pulls ahead of the moon. And the sun comes from behind the moon, or it comes from the east of the moon, and then crosses the moon, and we have the eclipse, and then it exits to the west. And that's one of the reasons that even though the sun and the moon go from east to west in our sky, the sun is actually pivoting on the moon, and as a result, the point of total eclipse actually moves from west to east. Okay? So let's go ahead and just have a look real fast at a couple of spots. The first one is going to be San Antonio, Texas. Now, the sun's going to be here, the moon will be here, and San Antonio will have a eclipse at about solar noon, which is going to be about 1:40 p.m. or so. Okay? Now, 45 minutes later, the sun is going to be over here, and the eclipse is going to be out here at Indianapolis, Indiana. Okay? And like I said, that'll be about 45 minutes. Now, 45 minutes transit to Indy, and San Antonio to Indianapolis is 1608 kilometers. Okay? Now, what's this angle right here? Well, obviously it's going to be the same as this angle down here. But this is going to be 0.315 times 0.75 because it's 45 minutes, and as a result it's going to end up at 2.36 degrees. Okay. Now, if we just do a real rough calculation, we realize that if we have an angle here, actually it's going to be easier to do it up here. If we have an angle here of 0.236 degrees, this distance, which is A, over the distance to the moon, will be the tangent of 0.236 degrees. Okay? Now, in order to get the actual distance to the moon, what we're going to want to do is multiply the tangent by the distance between the locations. Now, I'm going to use this for the tangent simply because this angle right here is going to be 90 minus 0.236 degrees. And the tangent of that angle is going to be up on the order of 180 or so. So let's go ahead and do this tangent. So tangent, angle alpha we'll call it, equals A over the distance to the moon. So what's the distance to the moon? The distance to the moon will be A divided by tangent alpha. See, we just have to multiply both sides by distance to the moon and divide both sides by the tangent. Okay, so let's go ahead and do that. So what's the tangent of angle alpha? Well, to do the tangent of angle alpha, we need to use the small angle scale on the slide rule, and it's 2.36, which is going to be, there's 2, there's 2.5, 2.3, 2.6 is going to be right about there. Okay, and that'll read down, and the tangent is now down here. So what we want to do is we want to go ahead and take that tangent, which is going to be for roughly that. Okay, and we want to divide that into the distance over here. So what we'll do is we'll go ahead and take 1608, which is here, and then we're going to multiply it by 435, which is going to get us over here on the C scale. Let's make sure I did that right. That doesn't really look right. I did something wrong here, unfortunately. All right, I know what we did. So 168. You know, this never freaking fails. This worked just fine. Am I doing that right? Yeah, that's right. There we are. Okay. So what we're getting here is about 390,000 miles, or 390,000 kilometers. However, this is not really correct. And the reason that it's not correct is that this is not the distance between San Antonio and Indianapolis, because the Earth is curved, all right? Indianapolis is actually down here. And as a result, we have to figure out this triangle right here. Now, in order to get this chord length, I have to know the radius of the Earth. Now, I did it with the radius of the Earth, but the problem that you run into is the only thing that we can reliably measure without knowing the radius of the Earth is the distance over the surface of the Earth. And that is 1608. Okay? Now, the truth is that this number is actually 1582. So it's really not that much of a difference. And as a result of that, no, it's 1595. I'm sorry, 1595. So it's only about 13 miles or 13 kilometers different. So we're not going to get too much of an error just using the surface distance. Now, what is this leg right here going to be? All right. This is where that 8 inches per mile squared comes back to bite the flat Earth, because that's what this is. And as we showed the other day, when you want to, you can get different leading coefficients, which is the 8 inches, depending on whether or not you're using miles, you're using nautical miles, or you're using kilometers. And when you use the 7.8 centimeters per kilometer squared for 1608 kilometers, this works out to be 202 kilometers. Okay, so our triangle now is 16, has a hypotenuse of 1608, and we have a distance here of 202 kilometers, and that means that this angle right here is going to be 17.16 degrees. Okay, and the cosine of 7.16 degrees equals this side A over 1608. Okay, so to solve for A, what we need to do is take the cosine of 7.16 and multiply it by 1608, and that gives us A. So the cosine of 7.16 on the small angle scale, or excuse me, the cosine of 7.16 is going to be pretty damn low. Okay, give me just a second, I'll tell you what it was. It's 109. It's 195. It's 190. It's 1592. So that's 1592. Now, with that, our distance is revised to 387,000 kilometers. And quite frankly, that's a pretty good estimate. The actual distance to the moon is 384,400 kilometers. When you use the chord length, by the way, you actually get 384,171 kilometers. So it's definitely within, a little bit over 200 kilometers of the actual distance. It was pretty remarkable. Okay, so now we know the distance to the moon. So let's go ahead and put that up here. All right. Now, in 300 BC, there was an astronomer by the name of Aristarchus of Samos who worked out the distances between the Earth, the Moon, and the Sun. And he did it in a very elegant way in a multi-step proof, and that's kind of one of the things that we're going to go over real quick. One of the things that he realized was that if we saw a half moon, that meant that the Sun and the Earth were perpendicular to each other in reference to the moon. Okay, so this was a 90-degree angle. And if he could calculate this distance, or this angle right here, he could get an idea of the distance to the moon, distance to the Sun in terms of the distance to the moon. So, for example, this would be the hypotenuse of the triangle. So the distance to the Sun over the under the distance to the moon would be the cosine of that angle right there. Okay? That angle equals 89.853 degrees. Okay? Now, the cosine of 89.853 degrees equals the sine of this angle right here. And that's a lot easier to calculate than a cosine that high. So we'll again go up here to the small angle scale. We'll go up to 1.47 degrees, which is going to be, or 0.147 degrees, which is there. And then what we will do is we will come down here and see where we are. And am I on the right scale here? Yep. That's 2.56 here. Now, if we divide 1 by 2.56, what we'll end up getting is the conversion between the two. So we'll come out here on the CI scale, go to 256, and our answer is 390, possibly 391, but we'll go with 390. So the distance to the moon over the distance to the Sun equals 1 over 390. So that is our second demonstration here. Distance to the sun over the distance to the moon equals 390. Okay. Now, by the same token, and pretty much for the same reason, if you look at the Sun and you look at the moon, and then you see out here at Earth, during a solar eclipse, the moon and the Sun are the same size, even though this is 1 and this is 390. That means that the Sun is 390 times the diameter of the moon. So the diameter of the Sun over the diameter of the moon also equals 390. Now, right now we actually can solve for a couple of problems. First of all, we know that the distance to the moon equals 387,000 kilometers, and we know the ratio of the distance to the Sun over the distance to the moon equals 390. All we have to do is multiply 387 or 387,000 by 390. So let's go ahead and do that. So here's 387 right there. And we will multiply it by 390. Actually, we're going to divide it by 1 over 390. And that gives us a distance to the sun of just over 150 million kilometers. Okay, so now we're going to put another thing up here. Okay, now we've got some other cool things that we can do. How big is the moon in relationship to the Earth? And how big is the sun in relationship to the Earth? Okay, this is kind of an interesting proof that I always liked. So we've got the sun, okay, and then we've got the Earth. And then at some distance out, we also have the moon. All right. Draw a line right through the center of all of those bodies. Now, the shadow of the Earth is going to come out like this to a point. Now, if you look at the sun, here's the radius of the sun, here's the radius of the Earth, and there is the radius of the moon. Now, if you look at the radius of the sun over the radius of the Earth, okay, you have a triangle here. If you look at the radius of the Earth over the radius of the shadow at the level of the moon here, you have a similar triangle. Okay, what's this right here? That's the radius of the sun minus the radius of the Earth, which is this part right here, over the radius of the sun. Okay? And that will equal the radius of the Earth minus the radius of the shadow of the Earth over the radius of the moon. Okay? Everybody with me so far? Well, yeah, it's not to scale, Richie. I'm just curious. You guys know what a racquetball is, right? It's about that, it's about, 2.5 inches in diameter. You play racquetball with it. If the Earth was the size of a racquetball, how far away would the moon be? It'd be like a meter away. It's really not that close. This point right here, where this cone of the Earth's shadow comes together, is about 1 million miles out, and the moon is about 1/5 the distance, or 1/4 the distance out to that point. Okay, so let's look at a couple of things. Now we can kind of break these up a little bit. So we have the radius of the sun over the radius of the sun, minus the radius of the Earth over the radius of the sun, equals the radius of the Earth over the radius of the moon, minus the radius of the shadow of the Earth over the radius of the moon. Okay? Next step. Let's get rid of all these negatives. So we'll add this over here, and we'll add this over here. Okay? And that'll get rid of it. So now we have the radius of the sun over the radius of the sun, plus the radius of the shadow over the radius of the moon, equals the radius of the Earth over the radius of the moon, plus the radius of the Earth over the radius of the sun. Okay, now the shadow of the moon during a total eclipse is 2.6 times the diameter of the moon. The radius of the sun over the radius of the sun equals 1. Okay? Did I do this right? All right, so let's go ahead and get a common denominator here. So what we want to do is we want to get the radius of the Earth times the radius of the sun plus the radius of the Earth times the radius of the moon, and we're going to put that all over the radius of the moon times the radius of the sun. Okay? So, what are we asking for here? We want the radius of the Earth over the radius of the moon. So let's go ahead and pull that out. So 3.6 equals the radius of the Earth over the radius of the moon, okay? Times something. Well, what's that times? Okay, this part right here is the radius of the Earth times the radius of the sun over the radius of the moon times the radius of the sun. So what do we have here? We've pulled out the radius of the Earth and we've pulled out the radius of the moon. All we're left with is the radius of the sun over the radius of the sun. Okay? Now, what do we have over here? All right, we pulled out the radius of the Earth, so we've got the radius of the moon on top. And then what do we have on the bottom? We pulled off the radius of the moon, so all we have left is the radius of the sun. Okay? Now, what does this actually equal? Obviously, the radius of the sun over the radius of the sun is 1. The radius of the moon over the radius of the sun, we already know the answer to that. It's 1 to 390. Now, the thing about it is that this is 1 plus 1 over 390. Essentially, this is 0. So what we're doing is we're actually multiplying the radius of the Earth over the radius of the moon by essentially 1 here, because this is just not very far off of 1. So, as a result, the radius of the Earth over the radius of the moon equals 3.6. So let's go ahead and add that to our list. Okay, so that's over there, and that's in our notes. Now the question is can we do the same thing with the sun? And as it turns out, we can. Let's go back. We're using exactly the same equations here. As a matter of fact, we're at this point right here. So we've got, this is going to be the radius of the sun over the radius of the Earth is what we're looking for. So we've got 3.6 equals the radius of the Earth times the radius of the sun. Plus the radius of the Earth over the radius of the moon, and this is all over the radius of the moon times the radius of the sun. Okay, what we want to solve for is the radius of sun over Earth, so let's go ahead and pull that out. So let's pull out the radius of the sun over the radius of the Earth. Okay, now again, here we have the radius of the sun, so all we're left with is the radius of the Earth. And that's going to be over, we've pulled out, did I do that right? Radius. I'm sorry, I did it backwards. That's the radius of the Earth over the radius of the sun. So what do we have here? We've pulled out the radius of the Earth here, so what we've got, let me just redo this here real quick so it's clear. 3.6 equals the radius of, let me make sure I don't do it again. Radius of the Earth over the radius of the sun. Okay? Now we're going to go ahead and pull out the radius of the Earth. We're left with the radius of the sun. We pulled out the radius of the sun. We're left with the radius of the moon. Plus what? We pulled out the radius of the Earth, so all we're left with is the radius of the moon. And then we've pulled out the radius of the sun, and all we're left with is the radius of the moon. Okay? So, all right. What's the radius of the sun over the radius of the moon? 390. What's the radius of the moon over the radius of the moon? Plus 1. So what we end up with is 3.6 over 391 equals the radius of the Earth over the radius of the Sun. Let's go ahead and do that real quick. So we've got 3.6. We're going to divide it by 391. Now I got that backwards. We're doing 391 divided by 3.6. Sorry about that. $109. So the radius of the Sun over the radius of Earth is 109. All right. So what else do we have to find out? How about how far away is the moon and the Sun in terms of the diameter of the Earth? Okay. So what we're going to do now is we're going to look at distance to the moon over diameter of Earth. Okay. Now, the way that we're going to figure this out is we're going to look at the full moon. Okay, so when we look at a full moon, which is in orbit around the Earth, the angular size of the moon is 0.519 degrees. Okay? So, the diameter of the moon's orbit is going to be 2 times the distance to the moon times pi. Okay? We divide that by 360 and multiply it by 0.519. Okay? So that would be that's what the angular size of the moon tells us. Okay? So we know the distance to the moon is 387,000. Okay? We know pi is 3.14. And then 2 obviously equals 2. And that's over 360 degrees. That'll give us the size of 1 degree, and then we multiply that by 0.519. Now, when you do the math on this, what you end up finding is that the moon is 3,478 kilometers in diameter. Now, once you know that, what else do you know? You know the diameter of the Earth. So what we do is we take 3, 4, 8, it looks like. Okay, and we multiply it by what? 3.6. Okay, in this case we're actually dividing it by 1 over 3.6, and that gives us a diameter of the Earth of a little over 12,500 kilometers. If we divide that by 2, we get a radius of Earth of 6,300 kilometers. And just for good measure, the diameter of Earth is 12,600. The diameter of the Sun is 109 times higher than that. So we go up here to 109, and we find the diameter of the Sun is 1,300,700 kilometers. We found a lot of information just from looking at a solar eclipse. All right, anybody have any questions? Well, yeah, of course it matches the spherical Earth. This is called a slide rule, Richie. This is Boomer Tech. This is an analog computer that was used prior to the onset of calculators. Calculators came out in 1972. Prior to that, all the way back to the 1600s, this is what they used to calculate things. This designed everything from the steam engine to the SR-71, or at least did the calculations for it. They're very nice. They don't require batteries. They were pretty accessible to a high school and a college kid. When the first calculators came out in 1972 that could actually do square roots and sines and all the special things that you can do on these things, they cost in today's money $2,400. And that was for the calculator. That was for a calculator that's not as capable as the one on your iPhone. Yeah, slide rules are pretty cool. One of the things about using a slide rule is you have to actually understand the mathematics behind it. They work on logarithms. So for example, the log of 2 is about 3.010, and the log of 3 is about 0.4771. Now you add those together. When you add the logs of two numbers, that equals the log of those numbers multiplied by each other. So, for example, if you set your slide rule here on 2 and bring your index out, and then add to it 3, you end up with a log of 6. So you multiply 3 by 2, you get 6. And they're really nice for trigonometry. Yeah, I mean, that's why I got this one over here. I'll show it to you. See that one back there? That thing's 7 feet tall. That's a classroom slide rule to teach high school kids how to use these things. And I'm a big proponent of them because they actually give you familiarity with numbers that you don't get by punching buttons on a calculator. You can get a very detailed answer very quickly on a calculator that's wrong. And have no idea why it's wrong. That's why I like slide rules. I like fountain pens too, but I also like computers and high-speed internet, so I'm a paradox. What can I say? I'm an enigma. Well, anybody have any questions about some of the stuff we went over? Yeah, you see this one right here? That's the 7-foot version of this little slide rule right here, a Pickett N500. This particular one is what's called a Pickett N3, and this is my daily driver. I like it so much I actually have 2 of them. So most Picketts that you'll see are in this, what they call eye saver yellow. I can't see these very well. I kind of like the ivory colored ones because I can read the numbers on them a lot easier. But there's a lot of them. They come, most of them are about 10 inches long. The longer they are, the more accurate they are. So for example, this one here's a 20-inch slide rule. You can see the difference. This one's good to about 3 significant digits. This one here will do 4 all day long. And upstairs I've got what's called a Fuller calculator that has a slide, that has a scale on it that's 41 feet long. And I can do 5 significant digits on that thing all day long, and sometimes even push it to 6. And then, of course, I've got an iPhone that'll give me as many damn digits as I want. Just depends on what I feel like doing at the time. Okay. I have a full class, by the way, in how to do slide rules on this channel, on slide rules in mathematics. That's why they call it slide rules in mathematics. But I have 7 or 8 videos up already that just take you from, hey, this is a slide rule, that's called a stator, and that's another stator, and this is called the slide, and that's called the cursor. It takes you all the way from that to how to do some pretty significant mathematics. And as you saw, you know, I kind of nailed some numbers here pretty easily. So, I mean, they're very capable little devices. The other thing that's really nice about them is you can use what's called tables and solving by proportions, which makes math a hell of a lot easier. You know. I'll give you an example of something. I'll give you an example of a table function here. Okay, so let's say we have a question on a test. Okay. There is 111 kilometers per degree of longitude. Okay. How many kilometers is 30 degrees? What is the radius of the Earth? And what is the circumference of the Earth? All right. Now, normally you'd have to do each one of these independently, but on a slide rule, all you have to do is you set 1 equal to 111, and then you just come out to 30. 3,330 kilometers is 30 degrees. The radius of the Earth is just over 6,350, and the circumference of the Earth is just shy of 40,000 kilometers, and we're flipping done. You know, because once you set that ratio up, all you have to do is just move the cursor around. You know, once this ratio is set up, whatever you do to this number, whatever number you have here, it does this to the number above it. So in other words, it'll take this number and it'll multiply it by 110. You know, 30 degrees is 30 times 110, so you get 3,330. The radius of the Earth is, you go out to 57.3 degrees and read straight up, and that's the radius of the Earth. If you go out to 360 degrees and read straight up, that's the circumference of the Earth. You just move that around a little bit. They're very handy little things. And quick. You can be very fast on these things. There are people, you know, I suck. I'm slow. There are kids in high school in the 50s that could do 75 extremely complex problems to within 3 to 4 significant digits in 30 minutes, involving squares of cubes taken to the 6th root. You know. See, here's another interesting one here for you that you might find fun. Okay, so let's take a little problem here. Let's take 127 or 128. Okay, let's take the square root of that, and then let's take the cube root of that, and then let's raise the whole thing to the 5th power. What's the answer? Would you even know how to do that on a calculator? Because that requires a lot of knowledge of the scientific calculator. So let's go ahead and see how to do that one real quick. Find the damn thing here. Okay. So on your log scales, what you do is you go out here to 128. There is 128. Okay. Then you realize that what this really means is that you take 128 to the 1/2, multiply that to the 1/3, and then multiply that to the 5th. The way exponents work is you multiply them together. So what you end up with is 1/28 to the 1/6 times 5 over 1. Okay? The reason I wrote it like that, you can also write it as 5 over 6. But this is how I'm going to do it. So, oops, here we go. So here we are on 1/28. Okay? And we take the 6th root of that, and then we raise it to the 5th power. And we read off our answer, 57. And the answer to that's 57. Check me on a calculator. Double check that. Sorry, that cursor's dirty right there. Figures. Just want to make sure I did it right. And 28. Yep, 57. But that's the sort of stuff you do with slide rules. So in any event, I'll go ahead and let you guys go. Thank you all very much for stopping by. Make sure you subscribe to this channel. This is my smaller channel. I not only have the full I will not only have the full series on teaching the slide rules. Next, we're going to be looking at cubes, squares, and their roots. And then we're going to look at the trigonometric functions, and then we're going to finish up with the log-log functions, which I just used. All right. Thank you very much. Who's here?
Kitty.
All right. My daughter just showed up, so I can put the thing back on safety now. I'm going to go ahead and say hi to her real quick. You guys have a good time. Thank you very much.